Thanks. So 20 minutes ago, you were asked to put axions out of your mind for a few minutes. And I'm going to ask you to keep those axion thoughts back a few minutes more. But I promise to say the A word at least once before I finish. So instead, I want you to think back to Therese's talk when she talks about the new LZ results. And what you heard is that liquid xenon experiments have been pushing down, scooping out parts of this plot over the last 20 years. And by now, we've managed to cover down to quite small cross-sections. What you also heard is that experiments running now, LZ and xenon n-ton, are going to push down about an order of magnitude more. But you can go still further. And if you build more and more sensitive experiments, eventually you stop seeing dark matter and start to detect neutrinos instead. And you get into what we call the neutrino fog, that I'll talk about a tiny bit more in a few minutes. And basically, Darwin's aim is to cover all of this space, all of the experimentally accessible dark matter space, down to the neutrino fog that we can cover with current technology. You've seen a few times how these TPCs work. I'm not going to bore you with going over it again. What's important for today is that we need to detect xenon scintillation light, and we need to drift the electrons up to the top of the detector to get our S2s, our second signals, which means we need an electric field. And we like our electric field to be quite uniform over the whole length of the TPC, so we know where our electrons are coming from. And so, with that, I can start telling you about Darwin. And our aim is to build a more sensitive dark matter detector using liquid xenon. That's actually conceptually very easy. All you need to do is make it bigger and clean it better. And it's something that we've been very good at. Over the last couple of decades, we've made our detectors a few orders of magnitude bigger. So you see that on the left plot in the x-axis, and even more than 3 orders of magnitude cleaner at the same time, measuring in terms of the radioactive contamination. So let's talk a little bit about how we do those things. And of course, it's not quite as simple as just putting a bicycle pump on xenon n-ton and starting to pump. But the result is kind of what you would imagine if you did that. So this Darwin detector looks very similar to xenon n-ton and to LZ that have quite similar designs. You see all the same materials, this very radio pure copper, the PTFE, which is very reflective for VUV light from xenon. And in our baseline design, at least, these 3-inch PMTs that we buy from Hamamatsu, it basically looks like a bigger version of xenon n-ton. And we want to put 40 tons of xenon in the sensitive region, which means 2.6 meters across, 2.6 meters tall, or something close to that. And all of the systems that we have now around it, so these muon vetoes, neutron vetoes, maybe water Cherenkov detectors, maybe scintillators like they have in LZ. And at the same time, systems to reduce the intrinsic radioactive contaminations. So let's talk a little bit about those, because the more difficult thing is not putting the bicycle pump there. The more difficult thing is making it clean. And all the current detectors are dominated in their electronic recoil background, which is the main source of background, but the one that at least we can discriminate from a little bit, because we can tell between the electronic and the nuclear recoils, by radon 222 and its daughters, and in particular the lead-214 daughter. And for Darwin, our aim is to reduce that background to such a level that we're actually dominated by neutrinos that it's very difficult to do anything against. That's something that we've been doing in the past, and we've already in xenon n-ton achieved this kind of 1 microbecquerel per kilogram level. We need to go another order of magnitude lower for Darwin. And I'll talk about some of the techniques we might use to do that in a couple of minutes. Also, in our nuclear recoils, we want to be dominated by neutrinos. And I promised I'd talk a little bit more about the neutrino fog and why it's such a big problem for us. And here you see the spectrum of energy deposits you get from neutrinos in blue, from solar neutrinos and atmospheric neutrinos down the bottom. And it's compared to what you would see from WIMP interaction for a variety of WIMP masses in black. And what you see is that solar neutrinos give you a signal that looks very much like our lighter WIMPs that we're sensitive to. Very difficult to tell between the two of them, even using the spectrum. While the atmospheric neutrinos look very much like the heavier WIMPs. And so once you start seeing these neutrinos in high amounts, then it's going to be very difficult to see a WIMP signal above them. Okay, so that's kind of the aim of what we want to achieve in Darwin. And there's a lot of R&D going on now to find ways that we might get there. And I'm not going to have time to talk about very much of it at all, but let me start by just mentioning some of the techniques we have to reduce this radon background that's dominating our ER background at the moment. And there's a couple of things that we already do. So you can try and just stop radon from ever getting into your detector or try to get it out completely. So we pick materials that don't emanate radon. And let me explain a little bit that the radon that's floating around in our xenon generally comes from the materials that we build the detector from. So there's radium inside all of our materials to some degree. When it decays, it releases the radon. And if the radon escapes from the material into the xenon itself, it can either directly enter the detector or come in through our gas systems. So what we can do is, first of all, just to look for materials that have a low rate of this emanation of radon. Of course, we do that already. And what I said we also already do is this online distillation, where using the different boiling points of xenon and radon, we're able to separate radon out of the gas all the time. And as long as you do this at a speed that's a little bit faster than the decay time of the radon a few days, then you can really significantly reduce the radon concentration and the radon background. And at the same time, we're looking at some new technologies, because it looks like these two on their own won't be enough for DARWIN. And there's some nice ideas that people are looking at in the collaboration. So one of them is putting a coating on your materials. And if you imagine putting something there that's thick enough to trap the radon after the radium decays, then it can't ever get into the xenon. And you only need to hold it there for the few days it takes for it to decay, right? It's able to diffuse out eventually, that's fine. But as long as you can slow it down for a few days, then it will never be able to get into the sensitive region of your TPC. So that's what you see in the top right here, this idea of coating materials. And finally, in a kind of similar idea, there's this idea of a hermetic TPC. So as I said, the radon is emanated from detector material surfaces. That means the rate of emanation is highest where the surface area is highest. And if you think back to what the detector looks like, on the inside it's this nice, smooth PTFE wall with some photomultiply windows and not much else. On the outside there's mess, cables, everything, field shaping rings, horrible stuff, and a much higher surface area. So if you can separate those two volumes hermetically, or at least reduce the flow between the two of them, you can reduce the amount of radon that's inside your more central, cleaner area. And this is really nice when you combine it, for example, with the distillation, and you just distill the inner volume. OK, I'm going to skip talking about PMTs, because I think people want to hear about some of the science we can do as well. And what I told you at the start is that we need to make a nice uniform drift field to get our electrons to the top. That does come with some technical challenges. So some of the other R&D we're doing is to build platforms that are the full diameter and the full height of DARWIN. So with this full height, 2.6 meter tall cryostat, we're able to experimentally show that you're able to drift electrons up the full length. So the idea there is that you need to have a good enough xenon purity and a good enough high voltage to get this field all the way up to 2.6 meters. And it's to prove these technologies. And the same in the diameter, so you're going to need to build some very large diameter electrodes to create your electric fields. And our electrodes, in order to not block the scintillation light that you also need to see, have to be very transparent. So there's some engineering challenges there. And with this 2.6 meter diameter, full diameter cryostat, you can test components like those electrodes before you install them in DARWIN. OK, and then in the last part of my talk, I want to tell you some of the science we can do. And by virtue of the fact that we're going to, in the end, be limited by neutrinos, we can actually do a lot of physics beyond just searching for WIMPs, which is very nice. So we can study the neutrinos that we see, and we can also do something like looking for neutrinoless double beta decay. And I'm going to talk about 4 of those that all of them I've been asked by at least one person about during the last 5 days. And start with the kind of vanilla WIMP idea, what the experiment is really conceived for. And of course, the idea is to push down towards this neutrino fog. So after 200-ton years of a similar experiment, and these limits come from the white paper, which was produced kind of in preparation for SNOMAS by the community. You get down very close to that. If you wait for a bit longer, then you can really push into the region where you expect to see neutrinos scattering on your nuclei. That's fine, but now let's talk about the more exciting other things we can do. So one of them, as I said, is to look for neutrinos double beta decay. And given the natural abundance in xenon, we expect to have about 3.5 tons of xenon 136 in our detector that undergoes double beta decay. And that would give us a peak at about 2.6 mega electron volts if we were to detect a neutrinoless double beta decay event. And so, of course, we're going to search for that in DARWIN and not achieve a sensitivity that's quite as good as dedicated experiments like NEXT and NEXO that you see on the right. But if you imagine an exposure of 10 years, where I've drawn the line to, you can actually get a sensitivity that's approaching the kind of similar level as dedicated experiments to search for neutrino-less double beta decay, just by repurposing the dark matter detectors. And now to neutrinos. So we're going to, in DARWIN, detect 1 neutrino every day, scattering off our electrons per ton of xenon. And we have 50 tons of xenon in the detector, or 40 tons in the sensitive region. So we're going to be able to see a lot of neutrinos. And that will let us, for example, put quite good limits on the probability of electron-neutrino survival coming from the sun, particularly at low energies, where there's a limited number of other experiments that are sensitive to those. And so you see that on the left, the error bar on the left for DARWIN kind of projections of what they'd be able to say about the survival probability is much smaller than the constraints coming from existing experiments. You can look at that on the top right in 2 dimensions. So obviously there's an anti-correlation between the weak mixing angle and the electron survival probability, if you prefer that parameter space. And I promised that I'd mention axions once more. So of course we can also look, we know from xenon 1 ton for solar axions, amongst other things, at scattering at low energies for us in our detector. And with DARWIN, of course, we'll be able to push down to somewhat lower sensitivities than existing experiments. Unfortunately, all we can do is make the experiment bigger, so we don't get very good scaling with the size of the experiment. We can't make a magnetic field stronger or something. But we will have a lower sensitivity to both solar axion and axion-like particle dark matter interactions within the detector, what you see on the bottom left. And you already heard this from a few people. We've recently, within the last year, started to combine expertise between the big experiments working with liquid xenon. So the xenon and DARWIN collaborations that already shared some knowledge, and now with LZ as well, and formed this XLZD consortium. So you can find us online and have a look at what we're doing. And we only really started recently to start sharing knowledge, but I think this is a very exciting for the future that will combine our strengths from the various collaborations. And that brings me to the end of my talk. I think you can expect some exciting results from DARWIN in 5 or 10 years or something. And in the meantime, of course, keep up to date with the experiments that are running now that are going to keep giving you exciting results looking for WIMPs in the meantime. Thank you.
I'm actually wondering about this XLCD. So is it the goal to build something faster or something bigger?
Something bigger, and definitely not faster.
Okay. So this is to go into the neutrino floor.
In the end, into the neutrino floor, it's a question of exposure, of time, exposure, and mass, of course. So if you build a 40-ton detector to get to the 1,000-ton-year exposure, that's the lower of these lines, you need, 20 years, 25 years of exposure. If you build something twice as big, then that reduces to something that's at least a little bit more appetizing, more like 10 or 15 years.
Yeah, thanks. I was just have a naive question about neutrinos. Here you we're saying that you get a lot of electron-neutrino events, and I always, I guess, thought of the neutrino fog as the point at which you start to get like a single neutrino event, but I didn't realize that there were a lot of electron ones already. So could you just help me understand, like, is it easy to distinguish between nuclear neutrino scattering electron one? Is there an S? Is it the one doesn't have an S2 perhaps? No, thanks.
Yeah, so I glossed over it actually, but it's exactly the same as what we do when we try to distinguish WIMPs from our electronic recoil background. So the electron scattering neutrinos will look exactly like the beta decays. That's our main background. And so we can calibrate. How do I use the pointer? There it is. So we can kind of calibrate that with beta decay sources. That's the blue band here. The neutrino scattering of nuclear recoils would look exactly the same as WIMPs with a smaller S2. And we calibrate that with neutrons. Okay. So it's just as easy as distinguishing WIMPs from our backgrounds.
Thanks.
So once you merge 3 experiments into one, how do you cross-check your result in case of discovery?
I guess that whether we merge our experiments into one or not, it would be very nice to have another technology confirm our result. And I think the best person to ask that is the liquid argon community. So it would be very nice to have a liquid xenon dark matter detector and a liquid argon dark matter detector both detect dark matter.
Excellent result, thank you.
I think that's even better than two xenon experiments.